All right, I do want to talk about the Hall effect. I'm not going to go into as much math detail as the textbook does, but at least the concept of the Hall effect. Because I think 1940s, maybe I'm off there. But for the longest time, we had this idea of current, we developed all this math, but we really did not know whether it's positive charges flowing or negative charges flowing. So is it a positive charge flowing in the direction of current or negative flowing in the opposite direction of current? And so a little experiment was conducted, and I'll oversimplify it. So I have a wire here that is exposed to a magnetic field coming out of the board. If I have a current that's going down in that direction, again, the two possibilities is I have a positive charge going down that way, or I have a negative charge going up this way. Now, it's happened been 19th century. Pre-Rutherford's experiment. All right, so well, let's look at the possibilities here. If I have a positive charge that is heading down, and we can set up a coordinate system just to potentially make the language better. I hat, J hat, therefore K hat's coming out of the board. So my magnetic field's in the K hat direction, my particle's moving in the negative J hat direction. What is the direction of the force acting on the positive charge? Right-hand rule could also be appropriate here. How'd you get that?
Curl it this way. Is it from? I can't remember if it was.
So you did a curl this way, like this?
Yeah, I don't. Is it negative or positive?
So what direction, your thumb is pointing in what direction?
Right.
No, I mean wide to the right. Or you let the fingers decide the direction of your hand and the thumb just happens to be pointing that way.
If field is coming out of the board and then current is down, I curl my fingers down.
Oh, so you did V cross V? V cross V?
Yeah. I can't remember exactly what this was.
The formula for the force is Q, V cross V. So you would put your hand in the direction of the velocity first and then go to V.
So negative I hat.
Negative I hat. Thereby also demonstrating that cross products do not, commutative property of multiplication does not work with cross products. All right, so the positive charge would be forced over to this side. So if positive charges were flowing, I would expect to build up with positive charges over here. Suppose I have a negative charge that's going this way instead. Which way would the negative charge be forced?
Towards the right.
Why to the right? How'd you get that?
Opposite of positive.
We can be more sophisticated than that.
B cross B. The other way now. Instead of that, it's that.
Okay, what'd you forget?
Oh, the charge.
Yeah, the charge is negative. So V cross B would indeed be to the right. However, the charge is negative, so it would be forced over here. So we now have a way to differentiate between positive charge flow and negative charge flow in the fact that if I expose it to a magnetic field, whichever charge is flowing is going to end up over on the left-hand side, which means that I would get an abundance of positive charges here or an abundance of negative charges here. Either way, if I looked at the potential difference from across the width of it, here I'd have a higher potential, this would be V high and this would be V low, and over here, this would be V low and V high. So we could actually, with the right equipment, determine which one is actually flowing, and it turns out it's the negative charge that flows, which is basically where we started in January. That's not to say I can't get a positive charge to flow. All I need is take some protons, expose it to a large electric field, rip the electrons off of it, and I got a bunch of protons. I think I can shoot the protons at a target, hey, and I got a positive charge flow. And that's the essence of so many high energy physics experiments. All right, questions on the Hall effect?
This might go too far, but, if we know the electrons are flowing that way, but what makes us, how do we know that, like, electrons are negative and protons are positive? Couldn't you reverse that? And then everything would still work?
All right, so, couldn't you reverse that? What sense do you mean reverse that?
Like, if we just called electrons, like, if we treated electrons as positive and then reversed everything else,
Oh.
and then, like, is that convention?
Yeah, you
or-
could potentially, let's say, if you reversed everything. So electrons are now positively charged and protons are negatively charged. Protons would still be in the nucleus. Definitely in classical physics, I think there would be no difference. We couldn't tell the difference. I don't think there would be a difference. Everything would be the same.
So it's just convention, I guess?
Yeah. It's like if you saw the world completely upside down since birth, is there a test that could teach you the way everyone else sees it? Just a thought. See, what I'm wondering here is the fact that cross products we call vector products, but it actually when you do a cross product, you get what's called a pseudo vector or an axial vector, because cross products don't reflect properly. If I've got a mirror here and I do a cross product, we'll call that A and B. A cross B would produce a vector in that direction, or axial vector. But if I looked at the mirror image of it, A cross B would produce a vector going that way, and a vector going this way is not reflected by reversing in that direction. So I was wondering if there might be something where you could tell the difference, but I don't think so. Got the reflection there, I got A coming out at us and then B going this way. So A cross B would be a vector in that direction. The reflection, A is coming up this way and B is going up. A cross B would produce one in the exact same direction. No, that is sort of a reflection. No, it's not. Air going this way would reflect going back that way. Anyway, it's the reflection that messes up why it's technically not a vector. But as far as we're concerned, it acts, smells, and tastes like a vector. The whole reverse thing just bizarre to me. Like there's a sugar substitute, and I don't know how far they got in the development of it, but
I've heard about that.
what's that?
I heard about that.
Where they changed, instead of making it a trans, it was with cis or whatever, the same
Yeah.
side or opposite sides, that one of them, your body will absorb and add fat, and the other one, it won't?
But it was too expensive to make, so,
Say it again?
it was too expensive to make, so we couldn't make it
Ah.
to the.
Okay. All right, other questions? All right. I've mentioned Maxwell's equations before. I'll write down what, sort of the summary of what we have right now. If I have the electric flux through a closed surface is equal to the enclosed charge over epsilon sub naught. We'll do the free space version. The magnetic flux through a closed surface is equal to 0. Indicate 0, and I'll go ahead and throw units in there, Webers. And then we have amp, so these are Gauss's laws. Or Gauss laws. That just sounds better than Gauss's. Gauss's laws of electricity and Gauss law of magnetism. And then we have Ampere's law. Which if I did a line integral of B dot dl, that's equal to mu sub naught times the enclosed charge. These, you have a three-dimensional surface here, you just have a loop in two-dimensional space, or I guess it could have been in multi-dimensional space, but just picture I've got a loop that connects up with itself, and I enclosed is the current that's flowing through that loop. We've also talked about Kirchhoff's laws, and one, the voltage gain of voltage gains and voltage losses around a loop is 0, and the other is the junction rule, that current flowing into a junction equals the current flowing out of a junction. And when I presented that, I made some passing reference to, there is seemingly a contradiction or an exception to that, but there's not really an exception, and that's what I want to address. So I'll take my DC power supply to a capacitor. And we've been working under this assumption that the current in equals the current out. So if I look at this point right here, I have some current flowing in, I have the same current flowing out. I have current flowing in here, I have current flowing out there. It seems to hold, except for the fact that I've got this gap right here. If I'm looking at this plate, my current flowing in, I don't have any charge flowing out of it. What I have is a charge flowing out of the other plate. So there seems to be an exception to the junction rule at this point right here. Well, we're dealing with capacitor. I know that the capacitance is equal to Q over delta V. Therefore, the charge is equal to C delta V. If I'm looking at that space in between, which is where I've got this potential difference, I got a potential difference across between them, I know that delta V is equal to the electric field times the distance between them. Obviously, a little bit of hand waving involved. I can also find the capacitance for parallel plate capacitor as epsilon naught A over D. So I can plug that in for my capacitance here. And so my charge is going to be epsilon naught A over D times ed. D's cancel out, and I'm left with epsilon naught A times E, where A is the area of the plate, the surface area of the broad side of the plate. what's the area times the electric field? It's a quantity we would have gotten to in the second week, third week, early on.
Is it the Gauss law?
Yeah, what's on the left-hand side of the equation, what's that called?
Electric flux.
Yeah. So this is just epsilon naught times the electric flux. Gauss's law still does apply here. I mean, we probably could have done this in fewer steps, but if I have my plate here and I look at a surface just on the outside of the plate, the only where there's an electric field is along this surface right here. There's no electric field in an ideal parallel plate capacitor. There's no electric field over on the left-hand side because it would cancel out with the electric field from the other plate. So I only have electric plate coming through this side over here, and so Gauss's law does apply. Now, if I want to figure out the current, I know dq dt is equal to the current, and so this just becomes epsilon naught times d dt by sub e. Now, this is not a physical charge moving. What is changing here is the electric flux. My area is not changing in this scenario, but my electric field is changing. So we have this sort of pseudo current, or as it's usually referred to, the displacement current, I sub d. And it allows us to still maintain the junction rule, just that the current coming out is not necessarily a particle moving, but it could be this electric field. And so Ampere's law gets adjusted here. When we're talking about current, we have our traditional current plus this displacement current. And so sometimes it's written as that, sometimes it's written as U naught I plus U naught epsilon sub naught d phi e dt. And that's a zero, not a Q. So this is Ampere's law with Maxwell's correction, sometimes just referred to as Ampere-Maxwell's law. And so it morphs into Ampere's, Ampere-Maxwell. So we now have three of Maxwell's equations. And again, Maxwell did not call them Maxwell's equations, that came later on. And then there's the fourth equation that we will get to in a few minutes. Any questions? I do want to point out parallels here. We have the electric field times the area, we have magnetic field times the area, we have magnetic field times the length. The question is there an electric field times the length? And the answer won't surprise you, it's yes. So there's a missing equation here, at least from a parallel point of view, of E dot dl. Let's do it. Let's figure out this last missing piece. '1820s, I believe. Faraday was playing around, as physicists are wont to do. He had an ammeter here, hooked up to a piece of wire. He had, over here, a battery hooked up to a wire with a switch. And he noticed that if you close that gap, that the ammeter needle is going to flick. It'll flicker and then go back to 0. When he opens this up, and that doesn't erase on this board, when he opens it back up, the needle flicks the other direction. You play around with it enough, you start to notice that there is a connection between this opening and closing and that needle moving. Now, when you close it, the needle flicks, goes back to 0, and will stay there until you opened up the circuit again. You play around with it long enough and you recognize, well, if my loop with the ammeter is like this, I don't get as much current as if it is like this. So there seems to be some connection between basically the area that is encompassed here. Also, the more powerful the battery, the greater the flicking over here is. And so you can realize that there's two major things that are involved in this. One is that the magnetic field that is produced by this matters, and the area of this loop of wire matters. And what quantity do we have that involves magnetic field and area? In unison would be really cool right now. It would make up for the dead silence after I asked it.
Gauss's law of magnetism.
Gauss's law of magnetism, although related, because you do have the V dot dA there, Gauss's law of magnetism is specific to a closed surface, and we do not have a closed surface here. But what is integral of V dot dA? Christopher, you look like you know it, you're just afraid to say.